for the most part, I have actually taught you all you guys need to know regarding transient analysis. So what we're going to do today is we're going to work one example problem, which is literally your in-class assignment. It's your first exposure to a problem that has more than one energy storage element. It's got two inductors in it. And then after we wrap that up, we have a lab to do involving transient analysis of circuits. So we're going to use break off into groups and use the equipment on the exterior of the room to take care of that lab and call it a day. So the problem that I've given to you guys for your in-class assignment is this one, where we have a 10-volt source connected to a 4-ohm resistor down here. We have a 5-amp source over which we have a voltage drop VCS of t. So this is the voltage drop over our current source as a function of time that we're interested in determining. We have yet another 4-ohm resistor up here. We have a 6-ohm resistor here. A 12-ohm resistor here. A 3 Henry inductor. And a 1 Henry inductor here. Okay. So in this problem, we have two inductors. It should be fairly obvious to see that they are connected in parallel, so we can combine them into a single equivalent inductance, which we'll do in just a moment. But I want to make a note here. I'm not asking you for the voltage drop or the current flowing through either of those inductors, but we are going to need to know the inductor's behavior at t is equal to 0 minus in order to successfully analyze the circuit at t is equal to 0 plus. If you've been staying current on your homework, you've probably experienced a couple of problems where you're not necessarily asked to find the inductor current or capacitor voltage, but you have to keep track of that in order to get your answer right. That kind of stuff. So I'm just kind of trying to reinforce that. One other thing here that appears I've neglected to draw is my switch. So I'll go ahead and do that while I'm thinking about it. And in this particular instance, our switch is closing at t is equal to 0. Okay. So because we don't need to know anything specific about either of the two inductors, I would argue that our first step in this problem should be to determine the equivalent inductance and replace our inductor network here with a single inductance, which will make this problem much easier to analyze. So if I identify my nodes here, I'm not going to bother identifying all of them, but I am going to identify these two in which my inductors are connected. Okay. So we should pretty easily be able to see that the 3 Henry inductor and the 1 Henry inductor are connected in parallel, right? So what's 3 Henrys in parallel with 1 Henry? Yeah, exactly right. 3/4 of a Henry, or 0.75 Henry. A question that I get asked a whole heck of a lot is, how do I replace these two inductors with that single inductance? Both of these inductors are between the red node and the green node. So I literally just take those two inductors out and then put the equivalent inductor between the red node and the green node. So to me, one easy way to do that is by going, oops, I need to make my pen thickness smaller. Right here. 3/4 of a Henry. As long as it's between, there's only a single inductance between the red node and the green node, we're good. But it is important to note that we shouldn't be replacing inductors with short circuits or anything like that, because that's going to mess up our analysis, right? So effectively what we've done here is we've taken those two inductors out and then connected the new inductance between the nodes where the old inductors were placed, which is really how we do any equivalent combination. Okay, may not just be obvious. All right, so we're now ready to analyze this guy at t is equal to 0 minus. So at t is equal to 0 minus, our switch is an open circuit. So we're going to have something that looks like this. Here is 5 amps. Here is VCS at 0 minus. And just for the sake of argument, I'm going to find my inductor current IL at 0 minus using this direction. I'm arbitrarily choosing this direction. It's only going to influence the value that the inductor current has at t is equal to 0 plus. So whichever direction I choose is correct. I just need to keep going with that direction in the next step of the problem. All right, so how could I go about analyzing this circuit to determine both VCS at 0 minus and IL at 0 minus? Carter.
So you don't have to worry about the 6 and the 12.
That is very true. The 6 ohm resistor and the 12 ohm resistor are effectively shorted out by the inductor for all time less than 0, because we're at the circuit is behaving as if it were a DC circuit. So as Carter suggested, we can completely and utterly ignore the 6 ohm resistor and the 12 ohm resistor and not lose any information whatsoever about the circuit's behavior. So I'm going to reiterate, how do we solve for IL and VCS? Hey, pardon? Nodal. I would personally feel that nodal is the better option than mesh here. And the reason I say that is because nodal will allow us to solve for the voltage drop over the current source without any extra work whatsoever. Whereas if we did mesh, we could pretty easily figure out what the current flowing through the inductor is, but we'd have to write a whole nother KVL equation later on to figure out what's going on with that current source. So I'm going to call this guy node A, and therefore has voltage VA. And I'm going to call this node down here at the bottom ground. And that's literally all that I need. Okay. So if I write a KCL equation at node A, what I get is VA minus 10 volts over 4 ohms minus 5 amps plus VA over 4 ohms is equal to 0. And I can solve this guy for VA, which will be exactly the same as VCS at 0 minus. So take a moment or two and solve this, verify that we get 15 volts. All right. So working with VA or VCS is equal to 15 volts, how do we determine IL at 0 minus? Right, so it's just VA over 4 ohms. So 15/4 is, well, I'm just going to leave it as 15/4 because I'm lazy. Anybody have any questions, comments, or concerns about the analysis that we've done here? All right, so now we need to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, we're going to have this guy. Our switch is now closed. This is 5 amps. Here's VCS at 0 plus, which we're interested in. We know that this current here is 15/4 of an amp. And from this point forward, we actually don't need to know what IL is doing for the rest of the circuit. We can only concern ourselves with solving for VCS and we'll get all the information that we need. Okay. So how do we go about solving for VCS? Anybody? We could do nodal again, right? I'm going to identify my nodes here. We're going to use nodal analysis. Some of you may be thinking, oh, well, let's use mesh. There's definitely 4 meshes in here, and none of them are current sources on the, and we don't have any current sources on the perimeter of the circuit, which means we're definitely going to wind up with 4 equations, 4 unknowns. While I know that I've probably convinced at least half of you guys to buy the calculator that can solve that system, 4 equations and 4 unknowns, I know that some of you are still rocking TIs and all that kind of stuff that can't do it. I believe nodal analysis will be good to get exactly what we're looking for here, but I just want to verify things by identifying my nodes. So this big thing right here is 1 node. This little guy right here is 1 node. This big thing here is a node, and this guy over here is a node. So we got 4 nodes. I'm going to purposefully choose to make this guy here at the bottom my ground. And I'm going to call this guy VA and this guy VB, with the understanding that my green node is just 10 volts with respect to ground. I don't need to really write an equation for that at this point, I don't believe. So KCL at node A is going to yield VA minus 10 volts over 4 ohms plus VA minus VB over 4 ohms plus VA minus VB over 6 ohms. This is all still the same equation. Minus 5 amps plus VA over 12 ohms is equal to 0. So to be clear here, I'm taking this current, this current, this current, this current, and this current. So there are 5 different branching paths out of node A. And I have 5 terms in my equation, so I believe I've taken care of all of them. KCL at node B is going to be simply VB minus VA over 4 ohms, VB minus VA over 6 ohms, plus 15/4 of an amp is equal to 0, where I've just taken into account this current, and this current, the 3 different currents that are leaving node B. I now have 2 equations, 2 unknowns, for which I can solve to determine the quantities VA and VB, where VA will again be VCS, but this time it will be at 0 plus. And I don't actually need to know VB for anything. So tell me what you get. I believe the answer is supposed to be 11.25, but verify it if you don't mind. .25, thank you. Anybody have any questions regarding the analysis that we've done here at t is equal to 0 plus? So let me ask you guys a question, and if you've looked at the answers on the in-class assignment sheet, then you probably know the answer to this, but do we need to analyze the circuit at t is equal to infinity? Absolutely. There are 2 sources that are left in at t is equal to infinity, so we have to analyze it at t is equal to infinity. So at t is equal to infinity. Oops, I'm going to have to do this on a new page. We have our 10-volt source, a 4 ohm resistor, short circuit, 4 ohm resistor, 6 ohm resistor, 12 ohm resistor. Our switch is still closed, so I'll draw that before I forget about it. Here's our 5 amp source. Here's our voltage that we're interested in. At t is equal to infinity, what do I do with my equivalent inductance? It's a short circuit. At t is equal to 0 minus and t is equal to infinity, our circuit is operating at DC steady state, which means we need to use the DC steady state equivalent for our inductor. So I would argue that we could still use nodal analysis or really just Kirchhoff's current law in this instance. To make it obvious why, I'm going to label my nodes again real quick, and this is just another way for me to make sure I'm not forgetting anything. So if we call this node VA and this node ground, VA is the only quantity we don't know, which happens to correspond to the voltage that we're looking for anyway, right? So KCL at A yields VA minus 10 volts over 4 ohms plus VA over 4 ohms plus VA over 6 ohms plus VA over 12 ohms minus 5 amps is equal to 0. VA will be VCS at infinity, which is 10 volts. By all means, take a moment to solve this system and verify. Any question regarding our analysis here at t is equal to infinity? All right, so we now need to determine the time constant for our circuit. For an RL circuit, we know that tau is the equivalent inductance divided by our equivalent resistance. Well, we already determined LEQ is 3/4 of a Henry by simply combining those two inductors in parallel. I feel very strongly that that is the same. Now we'll need to take our inductance out and then look in to a dead network. So if I turn off my voltage source, here's my 4 ohm resistor. Here's my 4 ohm resistor. Here's my 6 ohm resistor. Here's my 12 ohm resistor. I've made an internal mistake here. What did I screw up, Abigail? Right, so during the transient condition, the switch is supposed to be closed. So if I don't put this wire here, I'm doing it wrong. Okay. This is a fairly awkward looking network that I'm trying to determine the equivalent resistance of. So I'm going to take my time, identify my nodes and all that jazz, and go back to really kind of the third day of the class and determine the equivalent resistance seen between terminals A and B. So if this is B, this is A, let's call this guy C, then there's no way for me to go from A to B directly. I have to go through C. To go from A to C, I can go through the 4 ohm resistor or the 6 ohm resistor. To go from C to B, I can go through the other 4 ohm resistor or the 12 ohm resistor. So this is going to look like 24 over 10 plus 48 over 16, which is 2.4 plus 3, 5.4 ohms, if my mental math is correct. From this, tau is equal to 0.75 Henry divided by 5.4 ohms. And I believe this is 5/36. Please verify it if you got a calculator on. So what's left to do? Literally just plug our results into our generic equation, right? So I didn't need to go that far. V CS as a function of time will be whatever value it had at t is equal to 0 minus, what was that? 15 volts. For t less than 0 minus. At 0 plus, it was 11.25. At infinity, it was 10. So we will have 11.25 minus 10, or 1.25 e to the minus t over tau. So that's going to be the reciprocal of 536. So 36 over 5t plus BCS at infinity, which was 10 volts for t greater than or equal to 0. In my opinion, this question is probably harder than anything I will ask you on your exam. Joel. Sure. So we're determining the equivalent inductance and the equivalent resistance during the transient condition. The transient condition begins when the switch closes, right? So if we scroll up here way back to the top, look at our original circuit. The switch is open until closing at t is equal to 0. So once it closes is when our transient position or transient condition begins. So that's why the switch has to be closed when we calculate REQ. If we calculated REQ with the switch open, we would be determining the equivalent resistance of the circuit at DC steady state, which is of no use to us because that doesn't tell us anything about how the circuit behaves during the transient. Does that make sense? Effectively, yes. If you use the circuit at t is equal to 0 plus to determine REQ, you're always going to get it right. You take out your energy storage element, in this case, the equivalent inductance of 3/4 of a Henry, and look in through those terminals, and you're good to go. Any other questions regarding this problem? Skylar?
Are we ever going to have a problem where we can't combine those two inductors?
No, that's a very good question. In this class, if I give you more than one inductor or more than one capacitor, you have to be able to simplify it down to a single capacitance or a single inductance. If you cannot do that, then you no longer have a first order RL or RC circuit. You have a second order circuit, and they play by an entirely separate set of rules that we spend about 2 weeks exploring in circuits 2. So for this class, everything will boil down to a single equivalent capacitance or single equivalent inductance. If it doesn't, you literally do not yet have the skill set to be able to solve it. Any other questions? All right, so there is a homework set 15 that is available on Moodle. It is more transient analysis problems. In my opinion, those problems are difficult for the sake of being difficult. And let me explain, let me pull it up to explain what I mean by that. So if we look at this problem here, pretty similar to what we just did. We have, let's see, at t is equal to 0 minus, we have 3 meshes that we're interested in. I'm too lazy to count the number of nodes, but it's several. And at t is equal to 0 plus, we have 4 meshes and 1 less node. Analyzing this circuit doesn't particularly make you any better at performing the operations of transient analysis. It makes you better at applying nodal and mesh. If we look at problem 2, it's a similarly but even more awful problem that, again, literally doesn't do anything about you applying transient analysis principles correctly. It is just more practice in nodal and mesh. Problem 3, I would argue, isn't that bad. You could use it if you wanted to analyze things. But for the most part, I don't feel that these problems particularly add any value to homework sets 13 and 14. So I typically throw the grades on this homework set out. I encourage you to do it if you want the practice. You're not going to get any bonus for it or anything like that, but I'm not going to penalize you for not doing it if you don't want to go through the awfulness of the first couple of problems where you're not really learning anything new about what I'm trying to get you to understand here. Okay? So, all right. So with that being said, I'm done talking for the day. We've got about an hour and 10 minutes or so to get through this lab assignment. So let's get working on it.